Let's take a look at another way of determining the rate law for the simplest types of rate laws. Okay, we're going to look at rate laws where the rate is just equal to some constant k, your rate constant, times the concentration of R raised to the power n. So we're going to look at specific special cases where the rate law depends only on one reactant. Okay, and it is nth order with respect to that reactant, where n is equal to 0, 1, or 2. Because this is the most common type of rate law you would encounter. And we can also devise strategies so that when we run our experiment, the rate laws can be simplified into this form. Okay? So, um, if n is equal to 0, okay, what you'll find is a plot of r versus time is going to turn out to be equal to linear, and the slope is equal to negative c times k. Okay, and where does that come from? Remember, the rate of reaction is 1 over the coefficient of r, right, times the rate of consumption of r is equal to k times, if n is equal to 0, what would that be? And you say that's equal to k times r raised to the power 0, and r to the 0 is just going to drop out. Okay, this is what's called in math a differential equation. This thing right here. Okay, and when you solve this differential equation in math, you get a function. It tells you the solution to this will tell you how r depends on time. Okay, so r, you have two variables here, r, concentration of r, and time. Everything else there is a constant, and it involves what's called a derivative in math. And so when you solve this, the net result is you're able to figure out how r depends on time, how one variable depends on the other. Okay, so we're not going to go into detail as to how that's done. That you'll learn that when you do calculus. Okay, but the net result is that r is equal to some constant c times k times time plus another constant r naught. Okay, uh, so that's the equation that you'll get. And we're going to examine that equation in a little bit more detail in a little while. If n is equal to 1, okay, so the rate of reaction is 1 over the coefficient of r times the rate of consumption of r is equal to k times r raised to the power 1. Again, this is the differential equation, and if you solve that differential equation, you'll find that natural log of r would be equal to some constant times time plus the natural log of r naught. R naught is just the concentration of R at time 0. So that would be your initial concentration of R. Initial concentration of R. Okay? Similarly, if n equals 2, okay, the rate of the reaction would be equal to 1 over the coefficient times the rate of consumption of R is equal to k times the concentration of R squared, second order. Okay? And if you solve this differential equation, this is the expression you'll come up with. 1 over r equals a constant times t is time, plus 1 over r naught. Okay? So these are the expressions that you'll find. And I've written these expressions in the form that will allow you to see immediately what you can do to get the values for the rate constant. Okay? Now, C, like I said, here is the coefficient of R in your balance equation. Unless otherwise specified, we're just going to assume it's C. C is equal to 1. Okay? Because we can always adjust our coefficients for the balance equation so that the coefficient for a particular reactant is equal to 1. All right? So from now on, we can just ignore that C. We'll just take that as 1. Okay? So let's see what the consequences are of these. Let's go back to this expression for 0 order. Okay? You'll notice here this is equal to, if I were to plot R versus time, okay, then you can see I'm going to putting my R in my y-axis, so I can identify t as my x on my, I can put t on my x-axis. Okay, So I can identify negative ck as the slope of my line. So y equals mx plus b, right? So ck would be the slope of my line, and like I said, we're just going to say c is 1. So negative k is the slope of my line, and b is my y-intercept. So if you make this graph, okay, let's see. If you plot r versus time, if it's zero order, you get, if you plot your data, you're going to get a graph that looks like this. It's going to be a straight line, and the intercept, when time equals 0, the value of r is r naught. And if you were to measure the slope of this line, you'll find that that slope is equal to negative k. You'll get a negative slope, okay? And k is your rate constant. We're just going to assume, like I said, we're going to assume c is equal to 1, okay? So your slope is equal to negative k. So that's a consequence of, that would be what you would expect if your rate law is zero order with respect to concentration of R. What would you expect to see if it is first order? If it's first order, then what you'll find is this. First order, I'm going to rewrite the equation for first order. So for n equals 1, we say ln of R equals negative kt plus ln of R naught. Okay? That means if you were to plot natural log of R on your y-axis, and you plot t on your x-axis, then the slope you'll get is equal to negative k, so that's going to be your slope, and your y-intercept is going to be ln of r naught. So if I had data, okay, if I have r versus time, your data is actually going to look like this. R versus time is going to look like that. It's not going to be a straight line, okay? It's going to approach 0. It's going to be a curve. This is first order, n equals 1. But if I were to plot natural log of concentration of R versus time, what I'll find is my data is going to fit a straight line. All my data points are going to line up. And if I were to take, draw the best fit line through my data, I'll find that my slope is equal to negative k. Okay, and this y-intercept would be the natural log of R at time 0. Okay, so that's how you can tell that your reaction is first order with respect to reactant R. Okay, how can you tell if it's second order? This last one right here. So n equals 2. If you were to plot for n equals 2, again, if you plot R versus time, you're going to get a curve. Okay, oops. R versus time will give you a curve. Okay, so it's not a quicker way to check whether or not it is second order is to plot 1 over R, so 1 over concentration of R versus time. And what you'll find is if it happens to be second order, when you plot your data, what you'll see is that these data points, 1 over R versus time, are going to fall in a straight line. Okay, and your slope is going to be equal to k. Why is that? Because what's your equation? 1 over concentration of R equals kt plus 1 over concentration of R at time 0. So in other words, if I were to put this on my y-axis, 1 over R, that's my y, and put t on my x-axis, then I'll find that my slope will be equal to k, all right, and my y-intercept is equal to 1 over r naught. So this thing right here, the y-intercept would be 1 over r naught. Okay, so you need to plot concentration of R versus time. If it turns out to be a straight line, then you know what? If it turns out to be a straight line, then you know it's zero order. Okay? Basically, what this is saying is dr dt, the change in R over change in time is a constant. So it doesn't matter what your R is. If it doesn't turn out to be a straight line, it's going to look like a curve. Okay, then you say it can either be n equals 1 or n equals 2. It can either be first order or second order. The way you can tell is you plot natural log of r versus time. If that graph turns out to be a straight line, then you know it's first order. If that doesn't turn out to be a straight line, you can try plotting 1 over r versus time. And if that turns out to be a straight line, then you know it's second order. Okay? So let's take a look at these examples right here. Here's a plot. Here's the same reaction, data from the same reaction plotted three different ways. This plots r versus time. This one plots ln of r versus time. This one plots 1 over r versus time. Okay, so this is r versus time, ln of r versus time, and 1 over r versus time. So based on what you're seeing on the graph here, is the order of the reaction zero order, first order, or second order? Based on which graph is linear, you can tell whether the reaction is zero order, first order, or second order. Okay. Which graph is linear? The natural log plot is linear, so it's first order. Okay? If this was linear, then you would say it's zero order. Okay? Now, a very important warning about doing this in the lab. You'll notice that if you do not follow your reaction far enough, let's say you stop your reaction after this much time has elapsed, you might think it's linear. That graph is linear, right? So make sure you follow your reaction far enough so you can tell if it really is linear. So sometimes you could be tricked into thinking something is linear when in fact it's not. It just so happens you did not follow the reaction far enough. Okay. In general, you should at least follow the reaction so that your R has dropped by at least 75% or more. Okay. Uh, so um, so what that means, it's been cut in half at least twice. Okay, so if you start off with a concentration of 1 for R, follow it until at least it's down to about 0.25. That way, you can really tell if it's in fact a linear plot or not. Okay.